All right, class. Today we are looking at heat and calorimetry. So you should have gone through and done the majority of the experiment. And right in today's experiment, you had a couple of containers. We started with filling them each with different proportions of water. Right, one of them may have had water in here that was at I don't know, 20 degrees Celsius, and you may have had 50 grams of it. And in this one, maybe you had 100 grams of water at 50 degrees Celsius, right? And so looking at the ratio here, right, this would be a 1-to-2 ratio, or 2-to-1 if you look the other way. Um, and then we mix those together into a new container, mix it all up, and we want to know, right, what's the temperature now, right? With everything mixed together, what does that final temperature come to? You would have made some predictions, you would have looked at the actual outcomes, compared your predictions to those outcomes, and hopefully made some progress on today's lab. And one of the last things we had you do was we had you, instead of mixing water and water, you mixed metal and water. Okay, so in the very last thing, you had your stuff and you had your water, and you put a hot piece of metal in there, and then you needed to see, okay, well, what temperature does the mixture come to now with the hot metal in there? Um, and um, and you would have realized that this behaves nothing like the water and water mixture, right? If you were using an equation, right, you should have made a little equation to predict the water-water thing. If you use that to try and predict the metal-water thing, you would have found that it's completely and totally and terribly wrong. The metal behaves completely differently than the water, and it has to do with this concept called specific heat that we've talked a little bit about, but we're going to go into much more detail today. So specific heat. Okay. First thing is when you're mixing your water and water containers. I've seen students make a lot of different equations or kind of ways to think about this. Really, it's kind of like we're comparing a weighted average here, okay? So you have, I'm going to call, we have the mass over here, we'll call it M1. We have this mass over here, M2. This is at temperature 1, this is at temperature 2. And so, um, and then we want to mix them together, and we want to figure out, okay, well, what's the final temperature of all of this stuff? And what we're really looking at is basically a weighted average, where if you take M1 times T1, and then add that to M2 times T2, and divide that by the total amount of mass, M1 plus M2. That's why, so you kind of see how we're taking an average here. Weighted by the amount of mass that's riding in each cup and their temperatures. This will produce you the final temperature of the water-water mixture. Okay, T final. So this is one way to look at it. You may have come up with a different equation that works just as well. This is just one of the ways that I think about it. And when I'm mixing water with water, I could think of it as a weighted average, and it's kind of an easy way to kind of get around what's going on. So that's one method. Now, if you tried this method with the metal, it's not going to work, okay? Because when we're mixing just water with both substances being water, they have the same heat capacity, or they have the same specific heat. But metal has a different specific heat than water does. And what that means is, let's say I have some given quantity of water, okay? Let's say I have 100 grams of water. And then let's say I have the same quantity of metal, except for it probably wouldn't be the same size. It would be smaller. right? Because metal is more dense, right? So then I have 100 grams of metal, right? 100 grams of water, 100 grams of metal. And then let's say that I have, this is heat energy. That says energy. And let's say, now heat energy, we can measure it in joules. Well, and in fact, I think that in this lab, we do deal with heat energy in terms of joules. So I'm just going to call it a joule. Yeah, so we have a certain number of joules of heat energy. Okay, I don't know, let's say 50 joules of heat energy. Okay, well, if I put 50 joules of heat energy into the water, or if I put 50 heat energy joules into the metal, what's that going to do to their temperatures? Right? The change in temperature, what does that look like for each of these things? Okay, and so this is the important part, right? If you look at what are we keeping the same, we have the same amount of mass, the same amount of heat energy going into these things. So will their change in temperatures be the same? And the answer is no, right? The change in temperatures will not be the same. So which one changes more? And if we were to run this experiment, you would see that the change in temperature for the metal would be much greater than the change in temperature for the water. I'll put a little teeny arrow, right? Big change in temperature for the metal, little change in temperature for the water, okay? What that tells you is that the water has a really big specific heat or heat capacity, okay? But the metal has a small specific heat, okay? Or heat capacity. And what heat capacity is talking about is it's saying, if I have 1 gram of the material, how much energy, so how much energy will it take to change the temperature by 1 degree Celsius? That's supposed to be a question mark. Okay, so, right, this is what heat capacity is all about. If you have 1 gram of a material, how much energy does it take to change the temperature of that material by 1 degree Celsius? And for things like water, that heat capacity is a lot. In fact, so for water, it's 4.184 joules, okay, per gram degree Celsius, right? It takes 4.184 joules of heat energy to change 1 gram of water 1 degree Celsius. So for the metals, their heat capacities are much smaller. Something, depending on, each metal is going to be different, and you will discover that as you play around in today's lab. But these things are in the ballparks of like 1 point something or 0.8, right? Much, much smaller, right? It takes far fewer joules of energy to change the temperature, okay? So in the lab, we've a couple of times like asked that question, what is the difference between heat energy or heat and temperature? Well, this is the difference, right? The bridge, the thing that connects them is specific heat or heat capacity. Okay, that is the bridge between temperature and heat energy. You need to know what a substance's specific heat is to know exactly how much a given quantity of heat energy is going to change the temperature of something else. Now, another cool way to think about this, so let's say I have a glass full of water, okay? And let's say that this glass full of water, I don't know, let's say it's really hot. So let's say that it's 80 degrees Celsius, right? It's getting close to boiling. Well, if I have a piece of metal, and let's say that their masses are the same, let's say that this is 100 grams and this is 100 grams, and let's say that this metal is also at 80 degrees Celsius, okay, which one of these things contains more heat energy? And the answer is that the water does. Even though they're at the same temperature, the water has way more heat energy in it because for every gram and degree Celsius, right, you think about how much energy it takes. How much energy does it take to bring water up to, let's say they both started at 10 degrees Celsius. How much energy did it take to get the water up to 80? And if this started at 10 degrees Celsius, how much energy did it take to get the metal up to 80? Well, it took a very small amount of energy to get that up to 80. But to get the water up to 80, it would take a huge quantity of energy to get the water up to 80, right? So there's tons more heat energy stored in the water than there is stored in the metal, even though they're the same temperature. One of the ways that I like to think about specific heat is like it's kind of like mass, right? So imagine you have this giant boulder and you have this, I don't know, this little leaf. That's a leaf. Which one of those is easier to move? Well, okay, so I mean, this is obvious, right? It's way easier to move the leaf. And that's because it has a small mass, whereas the boulder has a huge mass, so it's much, much harder to move. Specific heat works the same way. Water has a huge, right? This is water, and the leaf is the metal because its temperature is easy to move, whereas the water's temperature is much more difficult to move, right? You can think about those concepts the same way. Okay, so earlier I gave you an equation that you could use to predict if you took two quantities of water and mixed them, you could use that little equation to predict the final temperature of the water mixture. Well, what happens if you take a hunk of metal and you want to put that into a cup of water, right? How does that work? How can I predict that? Is there an equation I can use to predict that? And the answer is that, well, of course there is, right? It's physics. This is an equation you can use to predict just about anything. So what is it? So in the lab, I gave you, you had this equation, right? Q equals M times C times T final minus T initial. So let's look at what each one of these things stands for. Q is heat energy, okay? M is the mass. C is the symbol for specific heat. Specific heat or heat capacity, right? And then this is the final temperature minus the initial temperature, or we're looking at the change in temperature, right? So how much heat energy does it take to change the temperature of a given quantity of mass? And that'll be based on what the specific heat of the material is, okay? So I've got an equation that kind of describes and defines this relationship. So what we want to do is, in a situation like this where we have the metal, well, we have two objects whose temperature is changing, okay? You're changing the temperature of the metal, and you're also changing the temperature of the water, okay? So it's like you have the Q from the metal, and you have the Q from the water, okay? Now, if the metal is really hot, then it's going to be giving up its heat energy. Okay, so I'm going to put a negative sign in front of the metal. Okay, and this is important, right? This is negative because the metal is really hot and it's losing heat energy to the water, right? The water is going to gain heat energy from the metal. Okay, so this is where we're set up, right? This heat is going into the water. Okay, so I've got the minus Q of the metal is going to be equal to the plus Q of the water. Okay, Sorry, it looks like a 3-year-old is writing this. Maybe my 3-year-old's handwriting would be better than mine. But this is important. So, right, these quantities are equal because where is the water getting the energy it needs to change temperature? Well, it's taking it from the metal, right? So the total amount of energy that the metal loses is equal to the total amount of energy that the water gains. Okay. All right. Well, now I can start filling some things in. So let's say, okay, here's my metal. Let's say I have 50 grams of metal at 150 degrees Celsius. And then for the water, let's say I have 100 grams of water at 20 degrees Celsius. Okay. And I want to know, when I mix the two, what will the final temperature be of the mixture? So let's run over here to our equation. So this is negative MC T final minus T initial is equal to positive MC T final minus T initial. So I have negative, the mass of my metal is 50. The specific heat, so this is gonna change depending on which metal we have. Let me just pick a random one from the simulation. Solids. Pick a solid. Let's do silver. And the specific heat of silver is 0.235 according to the simulation. And that's going to be times. Now, the final temperature, no, so this is important. The final temperature of the metal and the water will be the same, right? Because they're going to come and meet they're going to arrive at the same temperature, and that's when I know this is done, right? So I'm just going to leave this as T minus the initial temperature. So the metal started at 150 equals, okay, so the mass of the water, I have 100 grams of water times the specific heat of water, which is, I wrote that down somewhere. I might have erased it. 4.184. 4.184 times, okay, the final temperature, right, that's going to be the same for each thing, minus the initial temperature of the water, which is 20. Okay, now if you look at this beautiful thing, I have only one variable, so I can solve for that variable. It's just some not so fun algebra to get there. Right, so this side, the 100 is nice because this just becomes 41.8. Nope, move the decimal twice. 418.4, and then I would take that and distribute it in. So that's 418.4 times T minus 418.4 times 20 is equal to, and so here you can multiply these two things together and then distribute it in. So I'm going to have negative 50 times 0.235 T, and then a negative times a negative is a positive, so that's going to be plus 50 times 150 times 0.235. Okay, now to finish this off, this is negative, so I can add this quantity to both sides. This is negative, so I can also add this thing over here. So I can add this thing over here. And so I'm going to end up with, on the one side, we will have 50 times 150 times 0.235 plus 418.4 times 20 equals 418.4 T plus 50 times 0.235 T. Now, if you see, I've got T's here, so I can factor that T out. I'm just going to do that right now. So this is that times T, and then take this messy thing and divide it over. And now I've got something that I can throw into a calculator. And maybe you like to do your calculatoring like in the in-between steps, but I'd rather just do it all as one thing. So let's see if I can put this into my calculator without screwing up. 0.235 plus 418.4 times 20. So I've got that nightmare divided by 408.4 plus 50 times 0.35 close parenthesis equals, okay, so I am getting a final temperature of my mixture to be 23.55 degrees Celsius. And that makes sense to me, okay? And let me tell you why. So number one, I want to look up here and say, look, I'm still really close to the temperature of the water, right? I have twice as much water as I do metal. And if I look at their specific heats, look at this. Here's the specific heat of the water. Here's the specific heat of the silver. Silver specific heat is ridiculously low compared to the specific heat of the water. And so it's so much harder to change the temperature of the water compared to changing the temperature of the silver, that if you look at this in terms of degrees, right, the water's temperature only budged 3.5 degrees Celsius, but the temperature of the silver changed so much, right? Same quantity of heat energy, but totally different results in terms of like how their temperatures changed. Okay, so this is how this stuff works. If you want to see some more examples, let me know in the comments, and I can run a few more examples. But this is kind of the gist of this stuff. Good luck with this in the lab, and make sure to practice it for the final. And have a marvelous weekend, everybody. Bye.